17, and today we're going to discuss our DfM project, which is making improvements on the standard toolbox. The toolbox that we have chosen for our project is a multi-tiered collapsible container with injection molded compartments within it to hold various types of tools or crafting equipment. As shown in the middle picture, when the toolbox is fully opened, there are 3 levels total, consisting of a base layer and 2 collapsible levels with different size compartments that can be modified to the preference of the user. Overall, our predicted production volume falls at around 168,000 toolboxes per year, which comes from our benchmarking of similar products on Amazon. We have 2 types of customers that this toolbox can be marketed to. The primary customer for this product are mechanics, construction workers, and other professionals that are typically known for needing a mobile toolbox to bring with them to different sites. The secondary customer for this product would be people who enjoy crafting, and this toolbox would be used to store craft supplies such as beads, yarn, knitting needles, and more.
The toolbox comes with 8 parts: the base, small link, big link, supporting trays, divider A and B, the flaps, and the handles.
Alright, Israel's here. So here are our 5 diagram of our toolbox. So the task function of our toolbox is to manage tools, and there are 2 primal basic functions, which are firstly to transport tools and secondly to store tools. So for the basic function of this transport tools, especially we have to extend the handle, and for the store tools, we have to open and close the containers. And there's 4 main functions that we have to do, especially to assure dependability, ensure convenience, enhance product and place sensors. And those product tools and adjust configurations are our supporting function for each assure dependability and enhance products.
For this toolbox, we have created 2 fishbone diagrams. For sequence A, we start with the base, then we add our linkages, then we add the first layer of trays with divider A, we add the second layer of trays with divider B, and we add the flaps and the carrying handles. For assembly sequence B, we focus on the sub-assemblies, so we start on the left-hand side where we have a sub-assembly with 2 trays, 2 divider A's, a flap, a handle, and the linkage. We install that. Then we repeat on the other side. When we look at the sequence comparison table, we see that sequence B has a higher total value due to the sub-assemblies allowing for parallel work.
All right, Skylar here with the product analysis functional component mapping matrix. On the top row, we have the functions that our product will perform, and on the left side is the components that serve those functions. You can see that many components serve multiple functions, integrating tight, which indicates tight design, as well as the optional variants parts, the divider A and divider B, only fulfill their organizing tools function. This is because we're planning to have different variants that can organize tools differently. So having our components serve this specific functional purpose and nothing else allows us to keep our design modular for both variants.
Hello, I'm Walter, and this is our product's bill of material. Assuming that our manufacturing process was all done through sheet bending and injection molding and all assembled manually, also with the assumption that aluminum comes at 70 cents per pound, and that the average assembly worker is paid $17.50 per hour, our total costs are as shown. Not to forget to mention that our profit will be 20% of base margin, and that we will be selling 168,000 models per year.
For our quad chart classification analysis, we have no parts that are of low functional importance but high manufacturing cost, which is good. Our most expensive parts are our supporting trays and divider trays, which provide crucial organizing functionality. Everything else is low cost, and the important structural elements are also marked as high functional importance.
In the functional differentiation table, we can see that there are a large number of similarities between the 2 products, but also some important differences. For the most part, the functionality remains the same. Both products will store, transport, protect, and organize tools, as well as providing a gripping point and having the ability to open and close. The major differences are the product's ability to withstand impact, resist the environment, and the configuration that the product will be built in. This leads us to the component commonality table. The major structure of the product remains essentially the same. The trays, links, flaps, and all interfaces will be shared between products. The only components that will vary are the dividers within the trays and the base. To highlight the differences, we placed models of the two components that will be changing side by side. On the left image, we have two different trays. The left tray contains a much smaller compartment geared towards storing beads, sewing needles, and other small crafting supplies. The one on the right has two long, narrow compartments aimed at providing blue-collar workers with the space needed to store wrenches, screwdrivers, and other tools. In the images on the right, two different geometries for the base of the toolbox are shown. One is thicker and has rounded edges with the intent that it will be injection molded and is aimed towards the crafting audience, while the other geometry is made of aluminum and aims to withstand the tougher environment of the blue-collar worker. For our product family assembly diagram, we have two. The original on top shows the long, drawn-out process that was originally used. After our updates, there's a clear improvement from the original to the new. The new created two tray subassemblies that are common to both product variants, and it is not until it is time for the base to be attached that the two products diverge.